Hello everyone, welcome to the channel. This video covers top 10 must-know concepts of artificial intelligence. First, let us look into the entire flow of machine learning pipeline and quickly understand where each of these top 10 parameters or top 10 terms fit in the machine learning. Machine learning is part of artificial intelligence, meaning machine learning is a subset of AI. What is machine learning? Machine learning is a concept of machine that can learn to achieve goals on its own from data without being explicitly programmed. What we mean by learning and machine learning. Learning is about gaining knowledge by experience or being taught. So how does machine learn? A machine learns, let's say a machine like computer learns something about the structural descriptions from the raw data. Let us quickly look into the machine learning pipeline. The first step in machine learning pipeline is define problem statement. For example, identify car in a picture or identify a dog or a cat in a picture. Then collect relevant data like vehicles data, animals data, and then clean the data and label the data. Then feature engineer or featureization. Then comes model training, and after model training, evaluate the model performance. And then if the model performance is good, then deploy the model, else retrain the model. I have posted a detailed video on data labeling and machine learning pipeline and machine learning algorithms. The video title is ML Algorithms Basics for Beginners. I have mentioned the link for that video in this video description. If you are new to ML, then I suggest you to watch the machine learning pipeline and algorithms basics for beginners and then watch this video. Now let us start this video. What is featureization or feature engineering? Featureization converts string data into numerical data. In machine learning, we use many types of data: text data, audio data, video data, and image data. Why can't we just feed this raw data as it is in the form of strings to machine learning algorithms? Why we need feature engineering? The issue is machines like computers do not understand strings. Machines understand only numbers. Machine learning is based on mathematics, that is solving set of equations using linear algebra. The equations expects numbers as inputs, so we need a way to translate the raw data into set of numbers. For example, raw data would be iris data, IMDb movie data, or it could be data from internet. This data is translated into numbers and then converted into matrix form and vectors. Then machine learning processes this data in rows and columns by applying mathematical equations. Feature engineering techniques involve string handling and labeling the strings. Feature is any column value in the input matrix. We always try to predict the labels from the features. If you are familiar with data structures, then features becomes questions in tree. Let's understand feature engineering with an example. If we are classifying the vehicles, then features would be two-wheelers, four-wheelers, size of the vehicle, number of seats in the vehicle. For animals, features would be feathers, weight of the animal, and number of legs. What are the features in computer vision or in natural language processing? computer vision, feature would be edges, boundaries to detect objects. In text, features for sentiment analysis would be words like happy. Count how many times each word is repeated in the given text document. If word happy appears more number of times than the word sad or sorrow or dislike, then the sentiment of that text or customer reviews is happy, because the word happy appeared more number of times in the text than the other words like dislike and sorrow. Now, let us say if we are trying to predict the price of the house, then what would be the features? Can you guess? Features would be size of house in square feet, number of balconies, number of rooms inside house, price of the house in that locality. Feature extraction maps the real world objects like house to measurable quantities like size of house, price of house. This choice of features is crucial to the success of machine learning algorithm. Feature engineering is used more in linear regression. In deep learning, which is a subset of machine learning and AI, feature engineering is simplified with only basic set of natural features as system learns on its own in deep learning. Now let us move on to the hyperparameters. These are the parameters or configuration settings which are tuned to make neural networks train better and faster. Hyperparameters could be number of layers in the neural network, number of neurons, loss functions, regularization, learning rate, etc. We will look into the regularization learning rate in the next slide. For example, machine learning algorithms like random forest, the number of trees in the random forest are hyperparameters. If we take machine learning algorithms like decision tree, it has leaves or nodes or child trees. The depth of the tree, like maximum number or minimum number of observations in a leaf, are hyperparameters. For each proposed hyperparameter settings, the AI model is evaluated. The hyperparameters that give the best model are selected. There are two types of parameter models in AI. One is model parameters and the other one is hyperparameters. Model parameters like weight, bias are internal to model training, which are used for predictions. If you are new to machine learning, then weight is nothing but a numerical value. Let's say while training an AI model for identifying a fruit like apple, in a picture, weight for apple, which is red in color, could be 0.7. For apple, green in color, weight could be 0.3. Now coming back to the difference in model parameter and hyperparameters, model parameters like weight and bias are internal to model training, whereas hyperparameters are external to model training and are mainly used to improve the AI model learning process. Hyperparameter is the parameter of the model which is not learned as a part of optimization process. But hyperparameters need to be set or configured manually. Now let us look into model training and epochs. What is an AI model? AI model is structural description of raw data. What does a model contain? A model contains information extracted from raw data to predict unknown data. How does a model predict unknown data? Model applies rules on known data to predict unknown data. Set of rules could be in the form of a tree structure like decision trees or in the form of set of parameters for linear regression. Model training involves defining the goal or the objective or the problem statement, then processing the raw data, labeling the data, then send this data to machine learning algorithms like supervised, unsupervised, or to a neural network, and then evaluating the models against a set of goals or objectives. If the output of the model training matches with the objective or the input, then stop the training process, else identify the root cause of the mismatch in the expected output and retrain the model with new set of data or by changing the machine learning algorithm. How do we control model training? The input data set is divided into batches. Let's say total number of records are 100 and these 100 records are divided into 10 batches and each batch contains 10 records which are called mini batches. Then each mini batch passed over the AI model for training. A full training cycle of the entire input data set is called epoch. Model training is controlled by epoch. An epoch is a one complete training cycle over the entire input data set. There would be multiple rounds of training cycles, so multiple epochs on data set before the training before the model training converge. Next comes the two important concepts of AI output, bias and variance. AI models may unintentionally learn to produce discriminatory content from the training data. This is called bias. If the training data contains biased information, AI model might generate unreliable output. Bias could be gender bias or language bias or region bias or political bias. To reduce bias, the training data must include the data from various sources, data must be relevant to the problem statement, less assumptions about the data, and the data labeling process must be tested on various data sets. Now, what is variance? If the training data contains noise, AI model may learn from the noise pattern instead of learning patterns in the data. Noise could be a blur image, outliers, or incorrect labeling. Let's say a cat is labeled as a dog during data labeling process. If you are new to machine learning concepts, then do not get confused between biased data and noise data. Biased data is systematic error or a judgment error, like gender bias, meaning an AI model is trained to predict the scores of a competitive exam. The model is trained with more male data than female data. So the AI model prediction outcome would be more male data as the training data contains more samples and more examples and more patterns about the male data than female data. Whereas noise in AI model is random, meaning the data is incorrect, like the age of a high school student in the record is set as 99 years instead of 19 years. It's a error while entering the student record. Or an image of a dog is labeled as a cat and then the model is trained with this incorrect label. So how do we fix bias and variance? To fix bias, train the model with more complex data, more feature inputs, and then adjust the algorithm. To fix variance, train the model with less complex data and more accurate data with correct labels. Simple data cleaning should fix variance issues. If you are already practicing machine learning and familiar with the machine learning equations, then to fix bias issues, increase degree of polynomial, and to fix variance, decrease the degree of polynomial. Now let us look into underfitting and overfitting and how bias and variance are related to underfitting and overfitting. The data that is input to machine learning algorithms is divided into two sets. Training set, which is also called seen data, as this data is seen by the algorithm during training. Then another set is called test data or unseen data, as this data set is not seen by the algorithm during training. The training data is split into training group 80% and test group 20%. The data can also be split into training group 70% and test group 30%. Split could be two-way split, train and test groups. Split could also be three-way split, training group, test group, and the third group would be cross-validation group. There could be separate portion of the held out data used as validation data set during training. Let's say 70% training, 20% validation, and 10% test data group. Cross-validation data is used in cross-validation method to estimate how model generalizes on training dataset. There is no hard number for number of splits. Split the training dataset in n training groups and n test groups. Rotate the training and the test groups many times till all the variations of test and train groups are exhausted. We can choose the best model based on accuracy results of the test group, or we can choose the best model based on the accuracy results of held out group or validation group. Now let us look into the relationship between bias and variance and underfitting and overfitting. Underfitting has high bias and low variance, meaning AI model is simple and does not respond well to both training data and test data. Overfitting has low bias and high variance. A model responds well to the training data but not to the test data. Best model predicts well and generalizes well. Now let us move on to the next concept, learning rate. Remember the hyperparameters which we saw in previous slides? Hyperparameters ensure that AI model either underfits or overfits the training data set while learning the structure and patterns of the data. So hyperparameter is one of so learning rate is one of the hyperparameter. What is learning rate? Learning rate is the rate at which AI model learns the structures of the data with the updated parameters. Learning rate determines how fast the model parameters are updated for model to converge for best accuracy in less training time. Learning rate is a simple concept in AI. Learning rate of AI model is similar to the concept and steps that we take to learn new subject every day. Let's say you want to learn Python coding in 30 days. You can learn Python by spending 5 hours per day for 6 days, or you can spend 15 hours each day and learn in 2 days. You can configure the learning rate to 6 days or 2 days to learn Python coding in 30 hours. Similarly, while training the AI model, the learning rate is configurable. Too large learning rates will prevent the model from converging on an effective solution. Two small learning rates will take a very long time to converge. Therefore, we have to experiment with a range of learning rates in range 0 to 1, like 0.1, 0.01, and so on. Large learning rates takes less time to complete the training process. Large learning rates, unstable training that does not converge over time. Small learning rates take longer for completing the training process, but can result in stable training that converges over time. The best learning rate is determined by learning rate scheduler, batch size versus training speed, and the learning methods like RMS prop. We'll learn more about the learning rate scheduler in the next video. That is part 2 of top 10 concepts of AI ML. Now let us look into other hyperparameter, that is regularization. Regularization is represented as lambda. Regularization coefficients controls overfitting by making certain weights low. Low weights generalizes well to unseen data, that is new data. Regularization L1 drives all non-zero parameters towards zero. This is also called sparse model or lasso. L2 regularization penalizes large weights and decreases the value by 1. This is called dense model or weight decay. In L1 regularization, some of the absolute parameter values are kept low. In L2 regularization, some of the squares of the parameter values are kept low. In L1, some of the absolute parameters are low, and in L2, some of the squares of parameters are kept low. Now let us move on to the other simple topic, that is dropout. One of the method of regularization is dropout. As the name suggests, this dropout method removes some units from the neural network. This method randomly drops half of the neurons in each training cycle. Dropout technique is effective in image classification and natural language processing. A configuration setting of 0.5 for dropout is common in neural network. As a general rule, better to avoid dropout on the first layer of the neural network to avoid wiping out important part of the dataset. Dropout is computationally inexpensive way of regularization during model training. There is a drawback of dropout with large dataset. The drawback is as the training data increases, instead of decreasing the model training time, dropout may increase the model training time. This is due to the noise in the data, which is caused due to dropouts of neurons. Next, let us look into gradient descent. This is an optimization algorithm that can sense the low errors with regard to weights. Gradient descent measures the slope, that is change in error caused by change in weight. This helps in finding the next step in direction towards global minimum error. Accuracy or error is calculated for the given weights based on the loss. Change the model parameters to converge. If loss is high, then adjust the weights and calculate the error again. Repeat this step till weight values cannot be changed further and loss is minimum. And finally check whether the loss is minimum, and whether the model converge. Now the last topic is confusion matrix. Confusion matrix is basic tool for evaluating AI models. This metric helps in finding how much data is misclassified, that is predictions versus actual outcome. In confusion matrix, we have positive predictions, negative predictions, and then positive actual outcomes and negative actual outcomes. We can take positive predictions and negative predictions in row and positive actual outcomes and negative actual outcomes in columns or vice versa. To understand confusion matrix, let's take an example of classifying an email as spam or not spam. First row, first column is true positive. In this case, label was positive and prediction also positive. The classification is perfect in this case. Email is correctly classified as spam. First row, second column is false negative. In this case, label was positive, prediction was negative. This is also known as type 2 error. Predicting an email is spam when email is not actually spam. Moving on to the second row, first column. In this case, label was negative, prediction was positive. Predicting an email as not spam when email is actually spam. This is known as type 1 error. Next, second row, second column. This is true negative. Label was negative, prediction also negative. In this case, email is correctly classified as not spam email. One way to fix the type 1 and type 2 errors is by increasing the sample size. AI model performance can be analyzed in detail by tracking the type 1 and type 2 metrics. Models performance in terms of accuracy, precision, recall, and F1 score can be analyzed thoroughly by the counts of the predicted and actual results in the confusion matrix. We will cover the accuracy, precision, recall, and F1 score calculations in detail in part 2 of this video. I hope you liked the video. Please subscribe to the channel and let me know your comments. Thank you for watching.